Hi everyone, I'm Kartika from the Department of Biomedical Engineering, SMS College of Technology, Coimbatore. Today we are going to discuss about spontaneous fission in medical physics. First of all, what do you mean by fission? Okay, suppose we are considering uranium-235 will undergo spontaneous fission. If a neutron happens by, it results in two sizable nuclear fragments flying out, a few extra neutrons, gamma rays from excited states of daughter nuclei, energetic electrons from beta decay of daughters. Here the net result is lots of banging around. It generates heat locally, kinetic energy of tiny particles. For every gram of uranium-235, get 65 billion joules or about 16 million kilocalories. Compared to gasoline at roughly 10 kilocalorie per gram, a tank of gas, it could be replaced by a 1 mm pellet of uranium-235. Imagine. Okay. The enrichment is about the natural uranium is 99.27% uranium-238 and only 0.72% of uranium-235. Uranium-238 is not fissile and it absorbs the wandering neutrons. In order to nuclear reaction to self-sustain, it must enrich the fraction of uranium-235 to 3 to 5%. Interestingly, it was so 3 billion years ago. Now, the probability of wandering neutron hitting uranium-235 is sufficiently high to keep reaction crawling forward and towards. So the enrichment is hard to do, a huge technical roadblock to nuclear ambitions. Okay, here nuclear fission reactors, while coming into this reactors, nuclear fission is used simply as a heat source to run a heat engine. By controlling the chain reaction, we can maintain hot source for periods greater than a year. Heat is used to boil water. The steam turns a turbine which turns a generator. Here the efficiency limited by a familiar coordinate efficiency like the epsilon it is equal to TH minus TC by TH, about 30 to 40% typically. Okay, well, we are talking about the nuclear plant layout. This diagram, it shows the diagram of boiling water reactor power plant. Here, see this steel liner, the containment, and we have reactor vessel, pressure suppression pool, and shield building, steam, turbine, generator, condenser, pump, and the water flow. Also, we have the cooling water flow. Here, the steam is produced in the reactor vessel and flows at a high pressure to the turbine. After the steam is condensed to the water at the low pressure side of the turbine, the water is recirculated through the pump to the reactor core. The components of the reactor containment building are we have the exact components are the dry well, turbine, generator, condenser, and the steel liner, reactor vessel, and pressure suppression pool, and the water flow are to be discussed here. And the core of the reactor is this diagram shows the detailed view of a boiling water reactor core and the surrounding components. Here the components are we have reactor core first and the water, recirculation pump, jet pump, and recirculation pump. Also we have two-sided recirculation pump. We have feed water. From condenser, we have two ways, so we have two feed water pumps, and from condenser, we have to maintain the water level. We have steam separators also, and also we have steam line to turbine. This makes and this shows the detailed view of boiling water reactor core and the surrounding components. Okay, and this is an example. Here the rods contain uranium enriched to more or less 3% of uranium-235. Okay, here This diagram, it shows the control rod action. Here the concept is it need exactly one excess neutron per fission event to find another uranium-235. Here we have to insert a neutron absorber into the core. It removes neutron from the pool. Pulling out, and the rod makes more neutrons available here. Here the emergency procedure is to drop all the control rods at once. Okay, here we have an example, a local nuclear plant. Okay, here it shows, the curve shows the relative cost of nuclear power. Okay, and finally we have the finite uranium resource. The uranium cost is about $80 per kg, just a few percentage of cost of nuclear power. And also we have breeder reactors. For this, the reactors can be designed to breed plutonium-235 in a better than break even way. And also we have breeders. It could be used to convert all the available uranium-235 into 235 plutonium. Here the enough plutonium-239 falling into the wrong hand spills. It is pre-enriched to 100%. It needs less for bomb. See what happens if we are using nuclear reactors. It can lead to positive and also it can lead to a negative way. Okay, and also we have reactor risk. Once a vigorous program in the US, still so in France, 80% of the electricity is nuclear here. And orders of reactors in US stopped in late 70s. Also we have some failure modes, criticality accidents and loss of cooling, and the reactors are incapable of nuclear explosion, and the steam or chemical explosions are not ruled out meltdown. We have to assess the risk also. And here I've inserted some case studies for the nuclear power plant and nuclear reactor accidents in 1979. Nuclear waste, and we have storage solutions also, burial issues also there. Okay, in the next video we'll discuss about the fusion. Thank you.